Let's see if, there we go. I think that technology is working. I hope.
For now.
Yeah. I got to say, on homework 2.4, as a class, you did very well. Like, very well. I was very, very pleased with that. I thought that was worth mentioning. A couple of announcements. So, on Monday, so let's be clear, we're in Truss land, and on Monday, we're going to, so if you remember, I said that there was going to be 3 lectures dedicated to the method of joints. We're going to deal on Monday with how to solve a joint with 2 diagonals. And I think that for some of you, that might have happened on the homework. Because I think if you start at the very, very right of the truss, and you do joint C, and then I think it was joint B, and then you get to joint E, right? And there was 2 unknown diagonals. It's like, how do I do that? That's what we're going to talk about on Monday. And in order to do that, the easiest way to do it is to use matrix algebra. And if you bring your cell phone and use it as your calculator, it's probably not going to work. So bring a scientific calculator, graphing calculator, something like that. I see a number of you with your Casios, more than enough, okay? We're going to use the 2x2 solver in your Casio to do joints with 2 diagonals, okay? Because I'll be honest, there's really only 2 things left I want to show you with joints. We're going to do another example today that is just a little bit more on the bookkeeping side of things, because one of the things that you'll notice about the last problem that we did, as well as the problem that was on your homework assignment, was all of the truss members were inclined to the same slope ratio. So on the problem in class, they were 3 to 4, 3 to 4 slope ratios. And I believe on your homework it was 5 to 12, right? So they were all the same. That made bookkeeping a little easier. The example that we do today, that's not going to be the case. So you're going to have to put your thinking cap on and make sure that you've got that bookkeeping done accordingly. Now, I think probably what is drawing everybody's attention is this right here, right? Because you're seeing an indication of our first celebration of learning, right? What's wrong with celebrating?
We have a funny way of celebrating.
I'll bring the party favors. What's that?
Are you bringing cake or donuts?
I'm bringing party favors. The exam.
That doesn't sound like a fun party favor.
For you, for me, it's a blast. I'm kidding. So we're going to have our first exam on Friday, September 23rd, and it is going to cover classification, or at least the classification we've done up until now. It will cover reactions, and it will cover trusses. On Friday, next Friday, I'm not going to be here. But that's not just me. All of your engineering faculty should have canceled class on Friday, or they should be letting you know soon. The college is having a faculty retreat on Friday, and so none of us are going to be here. What I've decided to do, and I mentioned this last time, is I was going to do a recording where I discuss the project. I don't think that's a good idea. I think that if I did that, that recording would be fine, but then I'd be rushing truss deflections, and I don't want to rush that. It's a very easy concept to do, takes a little bit of time to understand. I'll say this, I think that of all of the topics that we do in here, truss deflections and deflections in general might be the first topic where as you start explaining it, you go, wait, what? You know, you might take a step back. Because I think up until now, everything from a conceptual standpoint has been pretty straightforward. Everything going up equals everything going down. What are the forces required to make that happen, right? That's simple. Deflections, a little bit of a different story. It also tends to borrow off of your knowledge of Engineering 216, mechanics of deformable bodies or mechanics of materials. So I'm going to take my time on the recording, I saw that. I saw that. I saw that. I know things about stuff. Yes.
Your dates are they're wrong on that last week.
They are?
Yeah.
Oh, they are. That's supposed to be 20, 22nd, and 24th, right? I'm sorry. You are.
That sounds like a form mistake.
That's like 0.35.
Does your mask on upside down count as a mistake too?
It is? Well, I'm not taking it off. We're just going with it now. That's what happens when you're rushing to class. So, all right, I'll flip it around. Now I'm going to be self-conscious about it the whole lecture. So that was going to happen at some point. See, these don't have the little bridge on them. So you could tell when you put the ones with the bridge on, you're like, there's something hitting my beard. So, all right. But yeah, so what we're going to do for this lecture is I'm going to sort of explain this process. And the name for the method is the method of virtual work. The execution of the method is really straightforward. If you understand how to solve trusses, then truss deflection is just solving trusses and plugging and chugging. That's all it is. But there's some theory behind it that I kind of want to take some time and explain. And I'll forewarn you that some of that theory is going to be a little like, whoa, what is he talking about? But I want you to rest assured that if it's a little wild, don't worry. The method is very, very simple to follow. Okay, let's go back to the previous lecture. And there's something I kind of want to focus on, and it's the number 2. Like, how do you have a whole lecture dedicated to the number 2? I don't, but you'll kind of see what I'm talking about here in a second. So let's go back to our assumptions. When we solve a truss, we make the following 3 assumptions. All of the members are connected by frictionless joints. The loads are applied at the joints, and all the centroids coincide. So the last 2 assumptions basically ensure that we are dealing with a concurrent force system, statics of particles from Engineering 213, and then the first assumption just tells us that there aren't any additional forces that we don't need to account for. And so what these 3 assumptions are telling us is that in a truss, the only forces are axial forces, either tension or compression. When we analyze a truss, we have 2 methods. The method of sections, which we're going to talk about that later. And we have the method of joints. Now, remember, when we solve the method of joint, or when we utilize the method of joints, we are limited to joints that have at most 2 unknowns. Why? Because we have 2 equations of equilibrium. We don't have 3 equations of equilibrium. We have 2. Okay? 3 equations of equilibrium will come into play when we utilize the method of sections, because with the method of sections, our forces will not be concurrent. They will not all be going through a common point. So that'll make our life a little easier. But that number 2, I want to see if that's going to pop up again. Let's just think about that. Now, one of the things that I kind of glossed over last time is I just assumed that that truss was determinate. Now, from an external standpoint, it was. There were 3 reactions, 3 equations of equilibrium externally. That was easy. But I just sort of barreled ahead, didn't really dig into it. We need to talk about that. Why do we need to talk about that? Well, first off, let's recap this. This was something we did. This was our first real lecture, right? When we looked at classification of structures. And if you remember, I said this is the degree of external indeterminacy, because what we're going to do later is look at classifying the internal indeterminacy of a structure. Now, let's just recap. So I sub E equals a pile of junk minus another pile of junk. And if you remember, those 2 terms, pile of junk minus other pile of junk, we're comparing the unknown quantities to the known quantities, right? We were comparing the unknown support reactions to the known equations. right? So R minus the quantity EC plus 3. Why 3? Because externally, there are 3 equations of equilibrium. Sum of forces in the x direction, sum of forces in the y direction, sum of moments. Now, remember this. If that value is negative, structure is unstable. But if the value is non-negative, either 0 or greater than 0, it should be stable, right? Should be stable and determinate, should be stable and indeterminate. And remember, there were some conditions for stability beyond just I equals 0. Remember, the reactions can't all be concurrent. You can't have all the reactions all meeting at a common point, because then you have a big old wheel. The system cannot withstand moments. The reactions also cannot all be parallel, because then you have a skateboard. That's external indeterminacy. What am I getting at here? What am I talking about? I want to look at this truss. This is an interesting truss. How many reactions are on this truss? 3. That. So if I put a bunch of loads on here, if I put a load here, and a load here, and a load there, could I solve for those reactions? That's no problem. That's easy. So this truss externally is stable and statically determinate. No problem. Now, let me erase these arrows here, because I want to go back to what I've been talking about here. Let's say I had these reactions. Let's pick a joint. I don't know, that one. How many unknown member forces are going through that joint? Oh, 3. What about this one? 5, 3, 3. Oh, where do we start? That's a problem, right? That's a challenge. This truss is internally indeterminate. We can solve for the reactions, but we cannot solve for the internal member forces by using equations of equilibrium alone. Now, let's be clear, okay? Do we construct indeterminate structures in real life? Yes, we do. There are reasons for using indeterminate structures. Indeterminate structures have redundancy. Indeterminate structures tend to be lighter. But indeterminate structures are more difficult to analyze. For now, we're not going to deal with indeterminate structures. Why? Well, in order to analyze a structure that is indeterminate, you must first cultivate the tools for determinate structural analysis. And by that, what I mean is you must understand the relationship between forces and deflections. And once you understand that, you can begin to start to attack indeterminate analysis. So we have to start somewhere. We always start when we're learning with determinate structures. But then that begs the question, how do we determine whether or not a truss is internally determinate or not? We need a formula. Well, let's go back to our concept. What were these I formulas all about? They were all about comparing the unknowns to the knowns. Let's look at this truss globally. What are the unknowns for this truss? The support reactions. And how many unknowns per member? 1. Why? Because the assumptions that we have made assume that there is only one type of force inside each truss member, an axial force, right? So the unknowns are M plus R, the number of members plus the support reactions, because there's 1 per member. Now what about the knowns? From an internal standpoint, we're talking about the internal equilibrium. At each joint, How many equations of equilibrium do I have? 2. This is the formula for the degree of internal indeterminacy for truss. M plus R minus 2J. What we're doing is we're comparing the knowns to the unknowns. Now, what we find is a similar pattern with indeterminacy internally with a truss than we do externally with a structure. In other words, if IT is negative, that truss is unstable. It just is. If IT is non-negative, the truss should be stable. It should be internally determinate or internally indeterminate. What's the deal with this should be stuff? What do you mean there? All right. Number one, for a structure to be internally stable, it has to be externally stable too. So if I go back to this previous example, right here, if I go back to this previous example, it wouldn't matter what the heck IT was if I removed this roller. Because if I remove this roller, the structure would be unstable. I don't care what IT is. So the first condition for stability internally for a truss is that it is externally stable. Beyond that, an IT being non-negative, and I'll admit this is the tricky one, and I don't really expect you to see this very easily, but the other condition is that the truss must be constrained against rigid body movements. That's kind of tough to see. I will blanketly admit that. But a dead giveaway that the truss is internally unstable is if you see something like this inside the truss, a region with no triangles. Because if there's a region with no triangles, the whole thing just wants to boop, kick over, okay? That would indicate an internal region of instability. If you ever have a truss that is internally unstable, if you're doing your math correctly, you will see it when you're doing method of joints or method of sections. Because you'll get answers that don't make any sense. You'll get, members that have infinite load or zero load, or members that you do one joint, it's compression, and the other joint's tension. The answers won't make sense. And if that's the case, sometimes you might want to take a step back and go, wait a minute, is this truss even stable? And if you start seeing stuff like this, that's a dead giveaway. To be clear, though, we're not in the business in here of constructing many trusses that are unstable. And I can tell you, if you're using a traditional sort of truss geometry and your IT value is non-negative, you're probably going to be fine. So one of the nice things about structural analysis software packages is they have ways to assess whether or not the structure is stable or not. It goes into linear algebra land that I'm not going to get into in here, but if you have a structure that's unstable, the model won't run. The program will get upset and it'll shut down. And we might talk about that near the end of the semester, why that happens. But questions? All right, I just want to do a little bit more practice on method of joints, and then we're going to call it for the day. I want to talk, though, a little bit about this truss. I have it, sort of pointed out here on the slide, so it's not like it's difficult to find. But as you look at this truss, is there anything that you notice about this truss that's way different than the one that we did in class last time, or the one that you did on your homework assignment? It's different angles, yes, but it's symmetric. Look, here's the deal. More often than not, engineers like symmetry, right? Even if the structure is complicated, go back to the images of the trusses that I showed you at the very beginning, right? Remember, there was that roof truss, and then there was that bridge. It was symmetric, right? The only time trusses in real life are not symmetric is if there is a good reason for it, like, for example, cantilever trusses. That's a good reason for a truss not being symmetric. But like a roof truss, no, it's going to be symmetric. Why? And let's be clear, when I say symmetric, I'm saying it is symmetric with respect to both geometry and loading, right? That matters too. Not only is the structure symmetric with the geometry, but the loads are symmetric as well. What does that mean from an analysis perspective? We only have to do half of it. That's important. Now, two other points I want to mention before we start doing the math. Look at this gray box up here. I counted it for you, don't worry. There's 21 members in this truss, right? So, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 20, and then the vertical member. So 21 members. 3 reactions, and there are 12 joints. IT is 0. I don't see any, sufficient lack of triangles. So this structure is stable and statically determinate. IT equals 0. For your analysis project, when you're going to be laying out this truss, one of the conditions I am going to enforce upon your truss is that IT equals 0. So you've got to ensure that. Now, before we begin this truss, we are going to find something very interesting about the internal force inside member DJ. Can anybody guess what the internal force inside member DJ is going to be? 0. That's correct. DJ is a 0 force member. It does not contain tension or compression. The internal force is 0. Does that happen? Yes. That happens in real life. It happens in real life for 2 reasons. The first reason is when you're doing truss deflections, we actually would solve this truss twice. We would solve the truss for the loads as they are, and then we would solve the truss for a single unit load where we're interested in finding deflections. So whenever you have a structure and you remove all of the attended loads and you only put one load on there, that can result in a lot of members being 0 force members. Okay? So that happens, and we need to be able to deal with it. But I don't want to give you this, mathematical, theoretical answer as to why there are 0 force members, because there is another reason why 0 force members are present on trusses. What do members in compression like to do? If members in tension like to yield and fracture, what do members in compression tend to do? Bend's not the word I'm looking for. It begins with B, but it's not bend. What was that? Buckle. Members in compression like to buckle. And so sometimes we will install elements that's only purpose is to brace the compression elements against buckling. It's not that they're carrying load, it's that they're ensuring that the compression member has adequate strength. Okay? So do we use 0 force members in real life? Yes. Yes, we do. Okay? So that's just me. I know I'm going off on a tangent here, I know. But I can't help it. You get upside down mass, Dr. Michelson, that's what you get. I want to know why these 3 highlighters keep popping up. That's what I want to know. Okay. Now, let me go ahead and just say something right off the bat. We're not going to finish this truss today. And that's okay. This is just practice, okay? You can obviously finish it on your own. What I want to do before we begin is this. I want to chart out the order in which we're going to do this problem. Let me give you an example of what I mean by that. Remember, this is symmetric. Would it make sense to start at joint A? Okay. Two unknowns. If I start at joint A, that's going to solve for those two members. My question for you is, if I solve joint A, which joint should I solve next? What's that? Well, you said G, right? Let's talk about that. Is there a necessity to solve G? No, because if I solve joint A, like let's just make up some numbers. If I get that this member has 27 kips in tension, what does this member have? 27 kips in tension. So as long as I have solved one side, I know what the results are over here. So I guess the best way of saying it is my first joint is either A or G, depending upon which side you want to do. Yes, sir?
So on the homework, do you want us to write them both? Like, we solve for AB, do you want to go ahead and write GF?
Not necessarily, because not necessarily. I'm actually going to show you what I did. This is my notebook for my calcs. And this is what I do, is I just say, here's the solution, and I say results are symmetric about the center line. Just leave it at that. I mean, at that point, I know, whoop, there's the answer. So no, you don't need to do that. That's a fair question. As long as you are indicating it in some fashion that you recognize it, I'm fine with that. That's a good point. So now, which joint should we do next? Okay, H will give us that and that. Now what's joint? There you go. Yep. Then and then C, yep. Then what's left? Just D, right? Now, that's a great point. We could solve D or we could solve J. I'm lazy. There's just a lot of arrows and I don't know. I don't want to do that. Let's just solve the one that's simpler. And let me say this. I think that there is credence to that from an engineering perspective. Don't make your task harder. Don't do that, you know. Do the easier approach. So, oh, I need to write that here. All right. So what we're going to do is we're going to follow this strategy, and we're just going to start knocking these things out. Now, before we do that, though, let's do some slope ratios. What's the slope ratio of these upper diagonals? Does anybody know what these are? 6 over 12. So 6 over 12, what's an easy way of writing that? 1 over 2. Yeah, so 1, 2, 1, 2, 1, 2. I know that's probably really tiny for you all. But yeah. What about these members? Like FK or BI? 1 to 1. Now this was kind of the whole point of the problem. And this one. Well, hold on. This is 12. What's that? So 3 to 2? Yeah. Which, by the way, if you just want to leave it 12, or 12:18 or 6:12, that's fine. Whatever's easiest. Easy, right? So now I'm going to do these joint analyses, and I'm going to do them probably kind of quickly, because I have found when I do these types of problems that once you get it planned out that this is the order I'm going to do it, I've got my slope ratios figured out, you can knock these things out really quickly. So let's do it to it. start off with joint A. There's the joint. There's that. Call this AB. What is it? AH. And 1, 2. Now I'll tell you this, and personally, I don't see there's a problem with this, but I don't, let's just look at it like this. This is 15 going up. What is that? Okay, just write it. I personally do not think it is absolutely necessary to go sum of forces in the y direction equals 0. That means that AHY is 15 kips going down. Just put it there. Did I do that? What? This is being recorded. What's that? If they heard me.
Your evil twin.
That's right. Dr. Gregson. Okay. What's that?
Is that the one that makes the mistakes?
There you go. All right. How about this? What is AHX? Can anybody just look at this and see if they can tell me what it is? 30. Now, you're getting ahead of yourself. So 15 down, the horizontal component is bigger, and it's 2 to 1. Just say 30. So if that's 30, tell me what's going on with this, completely what's going on with this. There you go. Boom. Now, here's another thing, and I'm fine with this. If you just want to do the Pythagorean theorem for all the diagonals at the very end, that's fine. In my opinion, this joint is solved. The only thing left to do is to write our answers on the big truss. So I'm just going to move on to the next joint. And what was our next joint? What did we say? H. Okay, so let's look at H. All right, so, oh, I hit my keyboard here. Okay, so H looks like that. There's that and that. 6 kips going down. Now both of these diagonals are at a slope ratio of 2 to 1. All right. Are there any of these that I know? Well, hold on. We know this one, though. I'm saying we know this. Let's write that out. That's what I'm getting at. I'm saying that this is AHX and AHY. Direction. Which direction do I draw AHX? To the right, compression, and this goes up. Exactly. And let me be clear, if you feel comfortable doing this, like the not standing on ceremony and just doing the joint analysis, I'm fine with this too. Just write it out, because it's not that complicated. What were you saying? You were saying something a second ago.
Oh, I was saying the only one we can solve for right now is the horizontal.
Okay, so what is it?
30.
30 to the
left.
to the left. And so what would be the name of it? HIX? Wait, I don't need that. So if that's 30, what's this? In what direction? Okay. So what's going on with this? 6, and it's 6 doing what? That was pretty easy, wasn't it? Now, something happened in this problem which we didn't really get into very much detail, but I kind of want to discuss. Remember AH and remember HI are collinear. They're along the same line, right? And not only that, but they're the same answer, right? 30 and 15 compression, 30 and 15 compression. That wasn't by accident. We're going to learn some techniques next time on how to identify zero force members. And one of the techniques that we will utilize is recognizing that collinear members, this will always happen. Now, where this wouldn't happen is if there's an additional diagonal. Then you start getting changes in your answers. But I'm just planting that seed into your head for Monday. What we're going to do on Monday is very clearly identify when that happens and when it doesn't. So don't try and get super predictive right now. Any questions? Yes?
So when there's a zero force member, how is it adding support if there's no force on it?
All right, that's a great question. The answer is, so the question was, how is this thing helping if there's no load on it? So let me answer your question two different ways. The only way that this would be a zero force member is how? If that load didn't exist.
Right.
All right. Now, to answer your question, this diagonal member, let's say there was no vertical. It's under compression. What do compression members like to do? Buckle. This is preventing that from happening. That's what it's doing. That's a great question. That's the kicker there. If you all decide or elect to take steel design, we will spend a great deal of time in there talking about effective length of columns and how column bracing affects capacity and whatnot. It's a big to-do in there. So I could talk about that all day. In fact, I do talk about that all day in there. So, all right. What was the next joint? B. Okay. Is there any load on joint B? Just the members. All right. Okay, let's see. Come on. So this goes like that, goes like that. Do I know any of these? This one, right? And this one. Okay, so this one, is it tension or compression? And this one? Wait, is that? All right, so Oh, I forgot the most important part. What is the slope ratio of that member? 1 to 1. It's not 1 to 2 like all these were. I find that that's like the one mistake that happens the most when doing these types of problems is you get into this habit of, oh, I've just been using 1 to 2 on all these problems. No, it's 1 to 1. So that's important. All right, help me out. What do I do? You tell me. The vertical. Okay, so what's going on with the vertical? Okay, and so it's 6 kips up. And if this is 6 kips up, what's this? There you go. All right, and the names, is that what? Is that, remember BI? Now, let's see if we're paying attention. What's going on with that member? There you go. I did that already. I already drew there. I'm just really cognizant about my arrows. I'll tell you one trick that I used to do when I was an undergrad and I was taking this class is I would sort of draw an exploded view of the whole truss, right? I would say like, here's a joint, here's a joint, here's a joint, and draw these little joints. Then every time I solved like a member, I would put the arrow in the opposite direction on the other member. And once I had it drawn out, I could solve the whole truss in like a couple minutes. Then it was just Pythagorean theorem, move on to the next problem. So, what's next? We'll do one more. All right. All right, so I'm going to cheat a little bit. Okay. Actually, let me put that right there. Okay, let's see. So we have, now there's a lot going on in this joint. All right, let's see. Now this one, 1 to 2, 1 to 1. This is where a straight edge helps. Now, this is probably the number one, I would say, thing to watch out for when doing a truss analysis is just the bookkeeping. Okay? Do we know this member right here? Okay. What are the values? Say it again? 30 and 15, because this member is that member, right? That's probably the hardest part, just making sure that you map your members one to one. So, and that's because that's HIX and HIY. Now, is there another member that I know? This one. What are its values? Tension or compression? There you go. All right, we'll do this one and then we'll call it. Now, What should I do first? Should I deal with verticals or horizontals? Horizontals, because I only have one here. What do I have? 30. I have 6. So what's going on with that? 24. This is 24 in compression. So if this is 24, what's that? All right. And that is member IJ. So that whole collinear thing I was talking about, that didn't happen here. See, here we had collinear members, they were equal. Here we have collinear members and they're not. The reason is the presence of this diagonal member. So just something to keep in mind, because when we start looking at zero force members, that's the type of stuff that you want to identify. Last, what's going on with that vertical? Let's see if anybody can see it. Wait, oh, I forgot to put the 6 kips on this. There we go. So what's going on with this vertical? Well, let's see. How much do we have going down? 6, 12, 24, 15 going up. So what is this? 9. Does that match what I have here? Yes, it does. Making sure I didn't add anything to my mistake counter. That was me being sassy. My wife would get a kick out of that. My wife and daughter, they have these matching shirts, and my wife says classy with a hint of, my daughter says sassy. I liked it. All right. Here's my advice, and it's advice. You don't have to do it. Do the remaining joints. When you get to the last one, you're going to get 0 on that vertical. It's going to happen. That can happen in truss analysis. That's okay. What we're going to do on Monday is our 2 remaining skills, I think, for method of joints. Dealing with 2 diagonals. So what happens when you have a joint and the 2 unknowns are diagonal members? Like, what if we got to joint I and we didn't know this one and this one? How do we solve the joint? Theory says we should be able to do it, but practicality says it kind of sucks. So we're going to sort of figure out how to do that. And lastly, we'll learn how to identify zero force members. Past that, Wednesday, we look at the method of sections. And then I don't really have anything else to teach you about truss analysis, like determining the forces. The remaining task is truss deflections. That's all I have. You all have a wonderful weekend. And that's from Dr. Gregson, the evil twin.